Okay, welcome back Science 10s to our next lesson. This is 2.4 and we're going to be looking at reaction types, and this is part 1 of reaction types. So now that we know what ionic compounds look like, molecular compounds look like, and we know how to write a chemical equation and how to balance it, now we're going to look at how to predict what reactions are going to follow and what products they're going to make. Now, although there's many different combinations of elements that exist and there's different types of reactions, we're going to look at some patterns here, and we're going to look at 6 kind of main patterns of reactions and what they're going to follow. And it often has to do with like pluses bonding with minuses when we're looking at ionic compounds. So these are the 6 that we're going to look at: formation reactions, which is also called synthesis; decomposition reactions; hydrocarbon combustion; single replacement, double replacement; and acid-base neutralization. So look at how reactions follow this pattern so we can predict what the products are or predict what the reactants were based off the products. And for this lesson, we're going to look at those first 3: formation, decomposition, and hydrocarbon combustion. So let's start with formation reactions. This is when we have a compound being formed, hence formation. So we have an element mixes with another element, and then we're going to get a compound, or those 2 elements bonded together. I wrote this as well as A plus B is equal to AB because, again, there's element A plus element B and they're bonded together as AB. It's important to note that this is an exothermic reaction. That means it's going to be giving off energy and the product is going to be more stable than those elements were on their own. An example of this is forming water. You take hydrogen gas and you burn it or react it with oxygen and you get a big kind of explosion with fire and a lot of heat, and then it creates water vapor. In this video here, we have a balloon filled with hydrogen. We bring up a flame, which is going to cause it to react with oxygen, just a little bit of that activation energy to get it to react with the air. And then we see a pretty big explosion that is pretty exothermic, as you can see, based off the fire and the light that is being produced there. Decomposition reactions are the exact opposite. You take a compound and you're going to break it apart into its elements. So I write it as AB broken into A plus B. Now this is the opposite. To undo that, we need to put energy in. So this is going to be endothermic. So formation is exothermic and decomposition is endothermic. An example of this would be if you were breaking water into its parts. So you have water. To put it back into that hydrogen oxygen, you have to run electricity through it, and this is called electrolysis. And we're going to break it into that hydrogen and oxygen atoms by themselves. But again, energy has to go in to do that. Now, the couple challenges to remember for when writing these reactions are that, remember, diatomic molecules. We're going to have some elements reacting together, and when they're just those single elements by themselves, they might come in groups of 2, or they might come in groups of 4 or 8, like we saw with phosphorus and sulfur. So we need to remember those if we have an element on its own. Also good to remember, if it's ionic, you need to make sure you balance your charges for that compound. So make sure you have the right subscript so that those charges are balanced. And if there's a metal involved in this reaction, it could be multivalent, meaning it has multiple charges that it could be, so like a +2 or a +3. And if you have like a formation reaction and it's like, say, iron plus oxygen goes to iron oxide, it doesn't say which is going to be that charge. It's going to be iron 1 or iron 2. So the top charge, the one that's on the top in the periodic table, is going to be the most common one, and that's the one that you're going to choose by default. So let's do an example together of write the chemical equation for iron reacting with oxygen. So I have iron, which is Fe, plus oxygen, which is O, goes to Fe and O stuck together. That's going to be your first step, just writing down the symbols, Fe and O, and then put Fe and O together. The next thing we have to figure out is the subscripts. So step 1 is the symbols. Step 2 is the subscripts. Okay, so for the elements on their own, like iron, we need to see if that exists just as iron by itself or if it comes in a group. Check the periodic table where it says polyatomic elements. It's not on that chart, so it just stays as iron. But oxygen is O2 on that group, so we have to put O2 there. It doesn't just come as O, it comes as O2. Now we look at Fe and O, and we need to look at the charges, and O is 2-, and then Fe is one of those multivalent. And it has a possibility of being either 3+ or being 2+. I think I misspoke before of 1 or 2, but it looks on the chart that is either 3+ or 2+. Now the 3+ is on the top, so that's the one that we're going to choose because that means that one is most common. So taking that, I'm going to put a 3+ here. All right, then to balance this out, I'm going to need 2 irons to get to 6. And then I need 3 oxygens to get to -6, and that one's all balanced. Now that we've done that, we've done the subscripts correctly and we've done the symbols, step 3 is we have to balance the equation. And I know that kind of sounds like balancing the charges, but this is balancing the amount of atoms on each side. can see that we have 2 irons on one side and only 1 on the other. So that's what we're going to need to have to fix here. I'm going to first look at the oxygens here because they kind of look the most complex. We have 3 in Fe2O3 and only 2 on the reactant side. So a common multiple to get there is 6. So I'm going to put 3 groups of O2, make 6. And I'm going to put 2 Fe2O3s there, and then we have 6 oxygens on both sides. Now I know how many irons I'm going to need. I need 4, so I'm going to put a 4 in the front there. So now I have balanced. There's one last step, and the last step for number 4 is that we have to put over here. Number 4 is we have to put the states. So iron on its own is going to be a solid. We see that on the periodic table, and it's a white square means it's a solid. Oxygen is a gray square, which means it's a gas. And then Fe2O3, we need to know that this is an ionic compound, and ionics at room temperature will be solid. So now we've put our states. That's step number 4. And we are all done there. Now, it might also ask if this is going to be exothermic or endothermic, or where you would put energy. This is a formation reaction because we have 2 elements added together to make a compound. We know that's exothermic, so you could either label it as exothermic, or you can put energy as a reactant or product. Well, if it is creating heat, heat is coming out, it's making heat as a product, so we're going to go plus energy over here. Normally it's not included with like the chemical formulas, but if it's asking what side energy goes on, it goes on the product side. Let's take a look at another one that says, write the chemical equation for how water is broken into its elements. I talked about this one already, how this one's gonna have to be endothermic. We're gonna have to put energy in there. This time we're starting with water, so I'm gonna start with H2O, and then it breaks into its elements. So we have to say what elements are in water. We see there's hydrogen, and we see that there is oxygen. So we just go H2O, to H plus O. Let's just put those 4 steps on the side. We've now put the symbols. Next, we have to go to subscripts. I actually already put the 2 there for H2O because I just knew that was the formula for water, and it's a molecular compound, and so we just know that formula from our knowledge of water, or if it was something like carbon dioxide, we'd use the prefixes. Now we're going over to the other side of H and O. When they're on their own, we check that chart, see if they're polyatomic elements, and they both are. H exists in groups of 2 and O exists in groups of 2. So now our subscripts are done. I checked that off a little too early. Now they're done. And now we're going to balance the equation. So make sure there's the same amount on each side. Our H's, there's H2 on both sides, which is good, but our oxygens are not balanced. We have 2 as a product, only 1 as a start. So I'm going to put a 2 there. And we have 2 oxygens off the start. But we notice that this also changed our amount of hydrogens. There's 4 on the reactant side and only 2 as a product. So I need to put 2 in front here to make that 4, and we should be balanced. So balancing is done. And the last step is to put the states. Water, we know, is going to be a liquid. If it was another molecular, you might not know, and that's okay. I wouldn't ask you to determine that unless it said so in the question. For hydrogen, we look up that, and it's going to be shaded gray on the periodic table, which means it's a gas. And oxygen, also a gas, and we are done there. But it could ask you about energy. We know that this is a compound breaking apart into its elements, which is decomposition, which is endothermic, which means we need to add energy to make this happen. So we need to add energy as a reactant to break it apart. So this is also known as endothermic. All right, takes energy to undergo that reaction. Next, and the last reaction for today we're going to look at is hydrocarbon combustion. So hydrocarbon means that it's a compound that has hydrogen and it has carbon bonds. So a whole bunch of C's and H's bonded together. Combustion means reacting with oxygen, which is an exothermic reaction. This is kind of another word for what most people think of as burning. When you burn wood or burn a candle, that's going to be combustion of those things. Now, if you have a pure hydrocarbon combustion, the products are going to be water and carbon dioxide. That's because we take the C's from the hydrocarbon, mix them with oxygen, get CO2. We take the H's from the hydrocarbon, mix them with the oxygen, and get H2O. So if you have pure hydrocarbon and it's completely burning, those are the products that you're going to get. So if you ever see a hydrocarbon and it says it's burning or reacting with oxygen, we know that those are going to be the products. Now, one of the harder parts about these are balancing them. So you have multiple compounds with the same element. Oxygen is going to be in both of the products. So you have to make sure the total amount of oxygens in the reactants is the total amount of the oxygens in the products. Remember, those are going to be in the water and the carbon dioxide. So let's do an example to show this. Let's say you burn butane, which is C2H6, okay? So it's a hydrocarbon, it's got C's and H's. I write C2H6. We have to know that burning is reacting with oxygen, so I get plus O. I'm gonna do the subscripts right now. As you saw from the other examples, O exists as O2, and it's going to produce CO2 and H2O. So I've got the symbols and the subscripts already done. So let's check those off, symbols and subscripts. Now I'm going to balancing. I'm just gonna switch to orange here so it's a bit easier to see. I'm gonna put my blanks in front here so we can fill them out. So I will go left to right here. Let's start with the carbons. There are 2 right here. So to get 2 over here, I need to put 2 in front. Two carbons. We're good so far. Next, I'm gonna go to H. There's 6 on that side. To get 6 on this side, they come in groups of 2, or an H2O. So I need 3 groups of H2O to get that. So I got 6 on both sides. Now, the tricky part is oxygen. I look over here and there's 2. I might look over here and say, well, there's 2 groups of 2, so there's 4. But we also have to look at the water. There's 3 groups of 1, and so we have 3 there. There's 4 over here in the CO2, and 3 over here in the H2O. We need all those to be on the other side for the reactants. So I have a total of 7 over here in the products. I need 7 in the reactants. Now you might think, okay, they're coming as groups of 2. How can I have 7 in groups of 2? It doesn't divide by 2 well. And that's true, and this is a new situation that we'll see with balancing hydrocarbon combustions. Let's just think, well, what if you did divide that by 2? You would need 3.5 groups of O2. So 3.5 times 2 would give you 7. I think, well, is that allowed? Can we put a decimal? You're not really allowed to put a decimal. So how are we gonna fix this is we're just going to double it so that it becomes a whole number. And I double that, I'm gonna double the whole rest of the reactions. So instead of putting 3.5 there, I'm gonna switch to green so we can see it a bit better. I'm going to put 7. So if I double the amount of oxygens, I need to double the amount of everything else so it stayed balanced, because 3.5 worked. That was everything was balanced on each side, but we just had a decimal. So I'm just gonna double them all, so now I no longer have a decimal. So the one people often forget about is this carbon was a 1. This for this C2H6 was a 1. There was 1 molecule of butane. So now I have to double that to 2. I think that's the most common one to forget about. So don't forget that. This 2 gets turned into a 4, and this 3 gets turned into a 6. So the balancing is probably the hardest part for hydrocarbon combustion. Make sure all the oxygens with CO2 and H2O are the same, and then we double it if we end up getting a decimal for the O2s. So it's a lot of work, but we are done balancing, and now we go to states. States usually not too hard. It should tell you in the question, it didn't show it here, but butane is a gas. She says that in the question. Oxygen is a gas, CO2 is a gas, and water, you actually have kind of 2 options here. Water at room temperature will be a liquid. However, we know that this is exothermic reaction, and so it often makes water vapor when things burn. So you put a liquid or a gas would be fine there. I'm gonna put a gas because it often does form water vapor. So now with those, I want you to try these 3 examples, pause the video, give them a try, and then play the video when you're ready to check your answers. Okay, let's take a look to see how you did. The first one, we just have carbon solid plus O2 gas goes to CO2 gas. That one fairly simple. It makes the molecular compound of carbon dioxide. So you know there's 2 oxygens there because it says dioxide, and we just put the elements carbon and oxygen that form it, and they are all gas. The next one, magnesium and oxygen, so Mg plus O2, because that comes as groups of 2, makes MgO. Now I knew it was just Mg and O because 2 plus and 2 minus there. Next for balancing, because we had those 2 oxygens, we needed 2 oxygens over here, which also made 2 magnesiums, so I had to put 2 over there. This is a solid. Oh, I forgot to put that this is a gas for oxygen, and magnesium oxide is a ionic compound, which is a solid. The last one, the combustion of propane. So C3H8 plus oxygen goes to CO2 and H2O. We need to know those are the products of hydrocarbon combustion. Next step was really balancing, because we knew most of those subscripts from either the question or knowing CO2 and H2O. And so I had 3 carbons, so I put 3 carbons. I had 8 hydrogens, so I put 4 groups of 2 to get 8 hydrogens. And again, the oxygen is the hardest part here. I have 3 groups of 2, so 6 oxygens there, and 4 groups of 1, there's 4 there. That makes a total of 10. Now, in the previous example, we had to get a decimal here, but in this case, 10 divides well by 2, or in groups of 2 oxygens. So we just put a 5 there, and we don't have to double everything in that case. Lastly, just put the states. Again, they're all gas. I put this gas for water because it makes water vapor, because we know it's exothermic. Those are the reactions you have to look at, but just before we finish the video, I want to talk about hydrocarbon combustion and some dangers of that. I said that pure hydrocarbon combustion, what's called complete combustion, when it has enough oxygen, makes CO2 and H2O. But if you have a limited amount of oxygen, you don't have enough O's to go with all the C's. And so you get either just C on its own, which is just carbon or soot, or you can see some black smoke, or you can get carbon monoxide, which is C with only one O instead of 2 O's. You know, where the carbon dioxide is normal, carbon monoxide is missing one oxygen because there wasn't that much oxygen present. This is a bad thing. This is a deadly, invisible, and odorless gas. You can't smell it, you can't taste it, but it can be being produced if there's a faulty furnace or something like that that doesn't have enough oxygen. So why is this really bad if it doesn't, we can't detect it at all? The reason that it's a problem is because it looks very similar to oxygen, which we breathe in and use to survive. And so this is what oxygen does. On the periodic table, it has a atomic number of 8. And so it comes in, 2 O's are bonded together because oxygen exists as O2. It comes into these red circles, which is a red blood cell. We're able to take it into the red blood cell, it distributes it through your body, gives the oxygen where it's needed, and then the oxygen goes away and the whole system works out pretty well. And it goes back to the lungs, get more oxygen, and the red blood cells are just delivering that. But now we have carbon monoxide, and this looks really similar to the oxygen. It's 2 molecules bonded together. One's the same O, which is periodic table number of 8, and then carbon is the periodic table number of 6, which means it just has 2 less protons. So it's pretty similar size, and again, it's bonded to an oxygen, so it looks pretty similar. But the problem is when it gets bonded to your red blood cell, it doesn't get used up by the body or by your muscles and stuff like that, so it just stays stuck on there. Now that red blood cell is kind of full, and it can't be taking oxygen delivered around your body. So it kind of is using up all your transporting red blood cells. So now you can't deliver the oxygen and it kind of suffocates you. You can still breathe in air, but you can't take the oxygen to your muscles and everything else from the blood. So that's why it's super dangerous, and that's why we want to avoid it, and you should have a carbon monoxide sensor. Lots are now built into your fire alarm. There's a carbon monoxide alarm in there, which is good, but it is good to check to make sure that you have one in your home, as we don't want any of this being produced inside where you're going to be. That's it. That's all I wanted to get through for this lesson. Tomorrow we're going to look at reaction types part 2, which is looking at the other 3 reactions. So make sure you ask me any questions in live time, try those practice questions, and I'll see you in the next video.